Righto, so yeah, my name's John Paterson. I'm project manager for the Phosphorus Mitigation project, and that particular role was set up about 4 years ago. I also work part-time for the Bay of Plenty Regional Council. I just want to acknowledge some of the science and sponsor people that we've been working with. How do we advance? Righto. So this project's been really well supported by academic institutions and funding partners. So you can see there's 10 funding partners there, including all the ag sectors and quite a few regional councils as well. This is sort of part of the start of Brian's presentation. So I'm using one of Brian's slides here, and I'll introduce him properly in a minute. So yeah, this work has just been done in the Rotorua area. I'm not going to spend time talking about what the issues are, because you guys are all working in this area. You know that eutrophication is generated by excesses of nitrogen and phosphorus, and particularly so here in the Rotorua catchment, where we're one of the first places in New Zealand to bring in limitations on farming intensity. So the focus of the Phosphorus Mitigation project is to look primarily at whether we can intercept stormwater and mitigate phosphorus from reaching Lake Rotorua. The farms are mainly regulated on their nitrogen attainment, and they've got caps to limit nitrogen and actually to progressively reduce their nitrogen losses to the lake. But today's focus is on phosphorus. So just a bit about the history of this project. Going back a couple of decades, the council put in quite a lot of things that were called detainment dams. So we refer to those as DDs. They're quite a bit different from what we're working with now. But there's about approximately 100 of those in place here. The main thing about them is they have a fairly low ponding capacity. And Brian will be talking about this ponding capacity. We measure ponding capacity by the volume in a structure relative to its catchment size. So the old DDs, or detainment dams, generally had a storage volume of about 60 cubic meters per hectare, and they had a continuous release pipe out the bottom of them. And with the detainment bunds, we have quite a different sort of setup, which you'll see. So this Rotorua attention to phosphorus started when I was with the council, and I set up the Rotorua P project. We're no longer allowed to call it the Rotorua P project because of associations with another thing called P. So that ran for about 3 years, and then council stopped the interest in that, and there was a period of time where we didn't make much progress until we brought Brian on board.
Sorry, John, can
I previously just talked a little bit about the old style detainment dams, which had a very low storage capacity, and they were done primarily for addressing downstream erosion issues. So about 2010, we started looking at the possibility of using the stormwater interception devices for dealing with phosphorus and sediment, rather than just for reducing peaks and reducing erosion. The key thing that came about during the 2010 to 13 period was the realisation that we needed to have quite a realistic, or a much bigger storage capacity than what we've had in the past. So we doubled it, and we aimed for 120 cubic meters of storage per hectare, and that's been the sort of the base point that the science has been wrapped around. And you'll see there that the first piece of science was done by a guy called Dylan Clark as a master's thesis at Waikato in 2013. And Dylan, unfortunately for him and for us, we didn't have a lot of funding, and we didn't have a lot of equipment, so we couldn't measure stormwater. And as you know, stormwater flows can be awesome, and to actually measure volumes to determine loads, you need to be pretty well geared up with equipment. So we're able to do that with the current project. So it was started in 2016. We have a governance board that's entirely farmers, and I'm the project manager of structures. And the project got funded from New Zealand Sustainable Farming Fund, and actually more than half the money came from our other 9 or 8, no, it's actually 9 co-funders now. So that's all the ag industries and quite a few of the councils. So Brian's challenge was to quantify the performance of detainment bunds. And I'll just quickly show you what a detainment bund is. It's just a temporary ponding on pasture. So we're doing this on some of the farmers' best paddocks, and it's essential that the farmers are happy to pond water. So in order to ensure that farmer buy-in, there's a guarantee that the water's not stored there for any more than 3 days. So these are prime pasture, gentle gradient valley floors, and you can see the water flowing through this one into a ponding area down below. This is one of Brian's set up with his apparatus, so I won't talk about that too much. This is just a sort of a couple of flow diagrams to illustrate roughly what we're doing. You can see the dirty stormwater arriving during a storm. You might note that the colour change in that graphic, so we believe that a certain amount of settlement of particles happens as soon as moving water hits still water. And Brian's going to talk quite a lot about the other factors going on there. So that's ponded, and you can see hanging down the outside of that pipe is a sandbag, and the farmer has the prerogative to empty the detainment bund prior to the 3 days. So with many storms, we get more water than we can store. So the riser on the end of the outflow pipe skims off the surface water, which we figure should be a bit cleaner than the other stuff. Anything that goes over a detainment bund during a storm will find its way to the lake.
The arrows in the last slide.
Oh, yep. Oh, right. Okay, so we've got some arrows on the downstream side going into the ground. Those are infiltration arrows, and Brian's just pointing out they're not quite appropriate in this slide.
In the ponding area it is?
In the ponding area.
You want to know that?
Okay, Brian, I think we're just about ready for you. This is just showing you the process of the detainment bunds. Emphasis on that 3-day period, so that we're working with the farm and the farming system, and that's a very important starting point. If we don't have farmers on board with this, we won't be building them. Right, O'Brien, I'm going to just hand over to you now. So here you can see the farmer there releasing the water after 3 days. I'm really rushing through this because what you want to hear is from Brian Levine. So Brian came to us from America, and we're just delighted to have him on board, and he's been working studiously for 3 years. We were warned about using PhD students. They don't always finish their PhDs. and the other thing is sometimes they fail. So I'm delighted to say that Brian finished his PhD on time, and it has been, what's the word you use? Defended successfully. So he's now Brian Levine PhD. Here he is.
Make sure my screen is getting pretty cool. All right, thanks for the introduction, John, and thank you for everybody joining us today to learn about this exciting edge of field nutrient mitigation strategy that's being developed here in in the Bay of Plenty, and hopefully with promising results could be expanded across the country. So as John mentioned, the strategy was previously found to have a proof of concept. Really the best data that came out of the master's project was finding that there was sediments that were being deposited in the pond, and when analyzing those sediments, it was found that phosphorus was bound to those sediments. So the strategy was preventing some amount of phosphorus from getting downstream, which was the goal. I was brought on board with lots of support from NIWA to set up the proper equipment to be able to tell what was coming into the ponding area and compare that to what was leaving the ponding area. And so here's an overhead field schematic of what my study areas look like. So starting at the top, there's that ephemeral stream path that was only flowing during storm events. We were lucky enough to be able to pick some sites where there was just a single main stream coming into the ponding area so that we could get an accurate enough representation of what was coming into the pond, and whatever data I'm showing for what came into the pond was corrected for any catchment that was downstream of that inflow upstream sampling area. So at both the upstream and downstream sites, collection sites, we had a flow meter and auto sampler set up that allowed me to analyze samples. And in doing so, collecting or being able to compare what was leaving the pond to what was entering. During the quick run through, we mentioned, or John mentioned, the water that was potentially leaving the pond during a ponding event. We referred to that as overflow, while at the end of the ponding period, the 3-day ponding period, when the plug is opened and water is drained at the base of that upstand riser, we call that release discharge. And hopefully in a couple slides, we've got some information pointing to the importance of talking about that. So here's overhead view of the Lake Rotorua catchment. My 2 study sites were in the northwest corner. Typically, this gets over 2 meters of rainfall per year. Important to note that these are well-drained soils, and the soils have high anion storage capacities to be able to absorb that dissolved phosphorus that's coming with the water that's infiltrating the soil. So any dissolved phosphorus getting into infiltrating the soil is going to be prevented from getting to the lake through the however, nitrate leaching is a huge issue here in this catchment. The groundwater is relatively toxic, and therefore denitrification does not occur, and the nitrates get into the lake. So really, this is a phosphorus mitigation approach here in this catchment. Just a quick overview of differences and similarities between the 2 sites that were part of my study. The Hauraki site was over twice as large. They had relatively similar pond volume to catchment area ratios, which is that important storage to catchment area ratio, which determined really the ability of detainment bunds to capture and store that water for that the runoff that was delivered to the pond and held for 3 days, hopefully avoiding excess overflow. Just for scale, the height of the bunds is there. They're usually between 1.5 and 2 meters. And I can't see what's on the far right there. Is anything on the far right? Nope. Okay. So I had a 12-month field study. Here's the hydrograph showing the 2 sites. The difference in inflow between the 2 sites was the result of more rainfall occurring during one event at the Hauraki site, and but both sites had similar number of ponding events, and 2 overflow events occurred, pointing those out on the graph there, just showing how much of the annual runoff that was delivered to the pond came during those two events. So, highlighting the overflow. Here is the runoff that's being delivered during a rainfall event. Water's going over the upstand riser, being released downstream. Ignore those arrows downstream because water or rainfall is still occurring in the catchment, that soil infiltration is very unlikely to occur to a significant extent. However, during the ponding, those arrows in the ponding area are appropriate because water is infiltrating those well-drained soils. Pictures at the bottom are that upstand riser before and after the height of the pond has breached the upstand riser height. So those two overflow events accounted for over 50% of the amount of runoff, suspended sediments, total and dissolved reactive phosphorus that were delivered to the pond. And that had hydrological implications for the performance of the bunds. So here we see the, okay, much better. So here in the green, we see how much runoff over that 12-month study infiltrated during ponding. Then in the yellow is the proportion of runoff that infiltrated downstream of the detainment bund. So that happened after the 3 days of ponding when the pond was released. Because of after 3 days, the soils downstream likely dried up enough to be able to allow that discharge runoff to infiltrate the soil. The blue is the amount of the annual inflow that went over the riser and was released downstream, and therefore likely to reach a connected waterway. That's important because that overflow is not infiltrating the soil, so any dissolved phosphorus is likely reaching Lake Rotorua. And the whole point is to prevent that from happening. So part of the detainment bund performance of preventing contaminants from reaching Lake Rotorua was the change in percentage of the concentrations of the contaminants as a result of the ponding. There we see pretty good changes in the suspended sediment concentrations, which is expected because of the decrease in the kinetic energy of the flowing water being able to carry those sediments. So during ponding, sediments are settling and being deposited in the ponding area. The difference between the total phosphorus is between the two sites was due to the proportion of sediment-bound phosphorus, more so being at the Oahu site compared to the Hauraki site, which had more dissolved phosphorus. Also mentioning the nitrogen there. We won't cover that too much. Important to note that the concentration changes during each event could have increased or decreased, although as a whole, the mean flow proportional concentration decreased overall during the year. However, due to that soil infiltration, the load of contaminants being discharged from the bunds decreased during each event. So here is what came into the pond in terms of the yields. Significantly more suspended sediments at the Oahu site, more total phosphorus at the Hauraki site because of the amount of dissolved phosphorus coming in. Here's the really exciting numbers, is looking at the loads that were prevented from reaching connected waterways. Roughly 1,000 kilograms of suspended sediments that were detained in the ponding area, and total phosphorus and dissolved loads. And the really exciting numbers was the percentage of each of the contaminants from reaching connected waterways. So that's a combination of what was prevented from being discharged in the ponding area, as well as what would have potentially been infiltrating the soil downstream. So these calculations, any sediments that were released from the pond could have been remobilized in subsequent runoff events. So the suspended sediments only takes into consideration what was deposited in the ponding area. So that's likely a very conservative estimation. For total phosphorus, that takes into account the amount that was sediment bound and what was dissolved. So these numbers are all accurate when taking into those differences in the forms of phosphorus and what could be remobilized in subsequent runoff events. Here's nitrogen. We'll skip over that real quick. However, we'll note that because of any nitrate infiltrating the soil will eventually reach Lake Rotorua because it will not undergo denitrification. It's really not a nitrogen mitigation strategy. And roughly speaking, only 10% of the nitrogen losses from the pastures in this area are being mobilized in surface runoff. The rest is being transported in subsurface runoff, and that's nitrate. So won't spend too much time on nitrogen. Important things that we found in the study. So was that the strategy was effective during those large overflow events. That's important to note because that is typically how the majority of contaminants reach the lake during a typical year. We found that the load decreases for the contaminants were roughly equivalent to the amount of runoff that was infiltrating the soil. And that highlights the importance of maximizing that pond volume to storage or pond volume to catchment ratio. This is important because that helps to avoid that excess overflow, which is essentially untreated runoff. And we also identified factors that might affect the long-term performance of the bunds and the management considerations that go along with that. And importantly, we assess the cost-effective nature of the strategy. And we'll talk about these things more in detail in the following slides. So one long-term consideration is the change of the Olsen P concentrations in the ponding area. We found that the attenuation of the phosphorus in the ponding area was causing the Olsen P soil concentrations to increase, and backcasting the performance and the data from my study year to the 6 or 7 years these bunds had already been in place, these numbers showing an increase in the concentration tracked very well for what we saw during my study. So we need to consider how to manage the phosphorus in the ponding areas. That should be considered in future research because we don't want the ponds to actually increase the concentration of the dissolved phosphorus that's being discharged downstream in the future. We also found that the repetitive ponding was decreasing the soil infiltration rates in the ponding areas. That's important because one of the main drivers that's causing the contaminants to be attenuated is that infiltration. So we see that the infiltration rates are a third, 50% to about 33% of what they are just outside the ponding area, which is evidence that the ponding is causing the infiltration rates to decrease. We don't know the cause of that decrease, whether it is the sediment buildup from those large loads of sediments that are being deposited, or just repetitive ponding that are changing the soil structure, or some combination of both. Depending on what's causing the decrease is likely to affect how you could potentially rehabilitate those soil infiltration rates. It could be as simple as aerating the soils. that's for future research. So exciting things is the cost-effective nature of the strategy. So roughly speaking, it costs about $10,000 to build detainment bunds. Then the added costs include an engineering fee, which in the Bay of Plenty is council enforced, the cost of the money to borrow money to construct a detainment bund, potential labor, repair, and maintenance, and potential loss of production from the ponding area. And it came to roughly $120 to $140 spent per kilogram of phosphorus attenuated in the ponding area for the study year. Also, that might actually be during the 6 years that the funds have been in place and projecting the numbers back. Sorry, I'm not too sure on that. However, the other benefits that were not included in the considered in the effectiveness was reduction in peak flow and flood management benefits from that, which lead to decreased erosion and downstream, benefits from reducing sedimentation and receiving surface waters, potential E. coli mitigation, which is a future study going on, and then benefits from aquifer recharge. Okay, so on to John, and he'll be talking about how to find where to put these effective, this effective mitigation strategy.
Change or you have your
Okay, Ron.
either or.
Okay, so first thing I want to show you is an output of the project. It's called the DB guideline. So it's pretty comprehensive, probably more comprehensive than we should put in front of farmers, but it was trying to summarize everything we've learned over the last 10 years. So we've done a short run of hard copy, and if you want that electronically, just come back and email myself or Jenny and we'll get that to you. So one of the key things that we need to talk about is how applicable are detainment bunds on New Zealand farming landscapes, and there's two ways we can look at that. We can look at a general applicability, and we can also zoom down into actual locations and where to put them. And then I'm going to cover the next steps with the detainment bund science. So that's the front cover of the manual or the guideline. There's a website there you can get it from, or you can just email us and we'll send it through to you. For strategists, for people who think, oh, this could be a good thing for us and for our catchments, we have made a detainment bund applicability model. So this takes a whole lot of, or 8 characteristics derived from GIS with LiDAR data, and it puts them into an algorithm and it spits out a result. It took a lot of work to get that algorithm tuned up, but the way it works is you take a bunch of sample plots, you request the slope data from and various pieces of data from that, put it into the algorithm, and it'll tell you plus or minus 6% how appropriate or how fittable detainment bunds will be to the target catchment. So it's really a planner's tool, and there's a paper on that you can look up, or you can just contact me if you want to talk about it further. Although we've tried to automate the process of selecting specific sites, we've tried twice to do that, and quite a lot of money's been spent in that area. We're yet to be able to automate the the actual location of putting these things in. So it gets down to needing to be still a manual process with people who are skilled with use of GIS and also have a really good understanding of landscape geomorphology and can, using the 1 metre contour layer that's enabled by LiDAR, you can get fairly efficient at picking these sites, and then we simply, as this diagram shows, we simply do a mock-up of a structure and look at the volume that will store and do that storage ratio. So in this one here, it shows it comes in at 122 to 1. 120 is the minimum threshold. The bigger the better. If they don't achieve that 120, then we try and look up and down that particular farmer's catchment. Is there a better site? So it's quite a lot of trial and error picking the best site, and it just involves hard yards using GIS LiDAR with LiDAR support. So what about the outcomes of this? Brian's data for phosphorus, I'll just talk about phosphorus. We've got quite a range of efficacy there, from 39% to 68%. So, you know, if we could treat entire landscapes, then we could say, well, yeah, we can reduce loads to water bodies by 39% to 68%. But in reality, there's an applicability factor which is dependent on the landscape. And we've done some whole landscape analyses, which I'll show you next. And generally, the applicability rate for most farming landscapes seems to be in the 50 to 70% category. I haven't done a farming catchment yet that's had better than 70% applicability. So if you multiply those applicability rates by the efficacy rates that Brian's found, and I've just averaged those to 54%, then installing detainment bunds can make quite a difference. Anything from, say, around 30 to 40% is quite achievable for a catchment that's installing detainment bunds. So that applies to phosphorus, but as Brian's pointed out, there's really good benefits for sediment as well. So this is just showing you a catchment in the Rotorua area. This is called the Hauraki Catchment. We've scoped that whole thing using Arc Pro, and we've made an Arc Pro project that speeds up the calculations and does some of the calculations automatically, but it's still a very manual process. So in this particular catchment, we've got about 70% of that whole catchment could be treated with detainment bunds. So if you multiply the efficacy factor of averaging around 54% by 0.7, representing the 70% application rate, you can see the bottom line there is that if everybody who could built detainment bunds in that catchment, we've reduced the load of phosphorus by 38%, and sediment similar, possibly a bit better than that. So what's next? We've been very fortunate to win funding from the MPI Islamic Fund. So we're now set up for the next 4 years, and I've noted the questions that have come in, and some of those questions I think will be answered by where we're going to next. So we've got the new project will have 4 trial sites, and the existing work has all been done on light free draining soils. So we've particularly targeted going to different soil types in New Zealand, and we have we've started discussions with setting up a satellite trial sites in West Otago with the Hauraki Catchment group, thanks to Craig Simpson, who's not able to be with us today, but I'm working with him. He's got some farmers that are pretty keen to progress working with us. And also up in Northland, probably in the Kaipara Harbour. And in both cases, we want to work on the heavy clay soils to see how things go when we don't have those good infiltration rates that Brian has pointed out are closely associated with performance.
So JP John Hampson is from Northland, and he's asked about the Kaipara Harbour sites.
So I'm liaising with Tom Stevens and one of his staff, Sarah, and they're working for us to identify an appropriate farm where we can set up a trial site. I understand it's most likely to be on the heavy soils side of the Kaipara Harbour, but it could be in another option that's been put up is to move south of Auckland into the what's that? Manukau Harbour, I think. Yeah. So as some of the questions have revealed, what'll happen on less well-drained soils? Well, we're going to find out. The other thing that we tried to bring into the first project, but the science advisory team said it was far too much work to put onto our poor US student, was to include E. coli, because E. coli is well known to be associated with sediment loss and storm particles. So we're going to look at the E. coli in the new project. Because we're anticipating that we probably won't get such good performance due to poorer infiltration, we've done quite a bit of work in looking into the possibility of using a safe and effective flocculant, introducing a flocculant. Max Gibbs at NIWA has been working on this for quite some years, and initially we're going to trial the use of anionic polyacrylamide, which sounds horribly chemical, but in fact it is used in some food additives. So we're pretty excited to be able to trial that. So on the heavy soil sites, we'll run them for a year without any flocculant to see what performance is like, and then we'll test the practicality. And it's got to be practical. It's got to be something that farmers can easily apply without needing a big dosing plant or something like that. So a lot of the new work is about fitting in with the farmers and the practicality of doing these things. The other area with the new project is we've noticed that there's quite a lot of surface shifted material, especially in the summertime with dung and sheep pellets and so on. So we're going to put up some screens and try and measure the buoyant load that's carried off on stormwater. Shall we deal with some of those questions now?
Just use it one computer and put
Yes, that's fine to have a question. So, yep, great.
So the first question that I noted was, could these things be installed downstream of forestry? So the short answer to that is absolutely. Because forestry itself is a really good dampener of high intensity storm events. We know that forestry cover probably dampens about 20% of the hydrology of the catchment. So our first priority wouldn't be to go to forestry sites, but there's a whole lot of reasons other than simply phosphorus that you might want to build detainment bunds, and we've certainly in our catchment scoping exercises we've covered the whole landscape, including forestry areas. Someone said that there's a grass that lives underwater, and would that make a difference to us? That depends on the farmers. Remember that we're going to farmers and asking them to commit some of their best pasture to these structures, and the water's only stored there for a very brief period of time. So having another species in that ponding area is a possibility, but currently we're just working with the existing farmers' productivity system and promising them that we won't be compromising their productivity system.
Okay, can you bring up the list there?
Yep, I've got them written down. There's another question was about the lifespan of detainment bunds, and this comes up at every field day. Every field day we've had someone will ask, oh, how often do I have to empty it out? So my standard response to that is, if you have to regularly empty your detainment bund out, there's something drastically wrong with the way you're managing your soil. So in Dylan Clark's experience and in Brian's experience, we're on pretty good farms with well-managed grass swards and minimum amount of bare soil. You shouldn't see a lot of sediment coming into your structure, and if you do, then the question goes back onto the farmer about the most important things he needs to do are his best management practice for managing soil and managing his pasture, and perhaps that's what needs to be addressed if you see quite a lot of sediment coming into your detainment bund.
Additionally to that, there was never, even though roughly 1,000 kilograms of soil or sediments were deposited in the ponding area, it's not like there was a pile of sediment at the bottom of the ponding area. There's zero evidence of that. After maybe a couple winter events, there was some coating of sediments on the grass, but yeah, still, it's not like there's just a 1,000-kilogram pile of sediment sitting at the bottom of the pond.
So, about plenty here, we're working on farms. Well, they're both dairy farms that the data comes from, and they're both farms that aren't really running winter crops. So it's going to be really interesting going down into West Otago, where there's the routine, putting in the crop of Swedes and grazing animals on fodder crop. We had one experience of that in the first thesis, and there was a really spiked loss from a paddock that was just upstream of the detainment bund. So we'll be looking into that a whole lot closer with down in West Otago, where we'll be seeing different sort of farming practices utilising winter fodder crops. Someone asked a question about the influence of soil type, Brian. So the infiltration, the porosity of the soil will be the main thing, but
so the effects of the ponding on soil. So yeah, well, no, I'm looking at the question. So how does soil type influence? So yeah, that's the well drained soil, how that affects infiltration rates, as well as the anion storage capacity of the soils, which is going to really be able to treat the dissolved phosphorus that's infiltrating or not. Just how the repetitive ponding might affect different types of soils. That sounds like academic research to me. What else?
Yeah. The next question was about, could we fill them with raupo and harvest the raupo? It'd be horses for courses. What we're trying to do is enable these things to be fitted onto high production New Zealand farms without compromising their farming systems. So amongst that, there may well be someone or a number of people that are quite happy to have more permanent water in these things and maybe have a different sort of crop. So yeah, that sounds fine, and I'm sure that someone will give that a go at some stage. We've just talked about moving on to clay soils, so that's a major focus for the next project. Brian's mentioned long-term effects on the soil and possibly that the soil pores may become more and more clogged over time, but we're sort of thinking about that and thinking of methods to re-aerate the soil. So we don't think that that's a long-term hurdle. I'm sure we'll find a way around that. Building them in series, we have done 1 or 2 in series, but I think if you can't achieve that ponding ratio in one place, then doing it in series is a possibility. But just remember the upper one, if it's got a low storage ratio, the water will come in and fill that up real quick, and it'll be overflowing and not really settle down until the next one. So I think having a singular ponding area is probably best, but if that can't be achieved, then having them in series is probably okay. It's just the extra expense of 2 lots of outflow structures and 2 and so on.
That's an interesting question, though, imagining using multiple bunds in series to come up with the same storage ratio. That's something to look into.
So from those questions, we've just got 2 others, one from John Beer, or one from Nadine. Can the BBs be placed on marginal pastures?
Oh yes, of course. Yep, you could take swampland, or you could take an existing dam. So it's achieving that storage, that peak flow storage is the main thing. Of course, with those marginal areas and maybe wetlands, again, we've got to look at that fact that they won't have the infiltration factor, and whether that we can get around the loss of performance with a simple and safe and practical introduction of a flocculant. So the flocculant will be a dry powder form that hopefully will be just easy to put out in bags that are laid in the flow paths.
Food safe, Alistair's asked?
Yes.
Or is it derived from plants?
Couldn't answer that question. I think it's probably more like it's a polymer. So whatever, Brian, it's a chemistry question. What's a polymer? We can, if you send me an email, we can send you plenty of information on that. No problem.
Al, and I think there was just another question from John. In terms of giving farmers info to make an informed decision, have you evaluated these against other types of mitigation?
So yes, I was hoping to find a table in this that is not actually there, and it's something I've taken out of the presentation because it doesn't show up too well. There was a study in the Bay of Plenty, or in the Lake Hauraki Catchment by Richard McDowell, that assessed the cost effectiveness of the existing mitigation strategies at the time, which was in 2010 when that study was done. I have since added the Detainment Bund results to that table, and that is now in my thesis. So perhaps stay in touch with John and you can get access to that when that's published, which was recently finally submitted in its final version this past week. So that takes a while to come around. As in terms of edge of field mitigation strategies, detainment bunds were the most effective and the most cost effective. Best management practices for fertilizers and erosion management, those are the best practices. But in terms of edge of field, at least with my studies and comparing it to other strategies in the Lake River catchment, detainment bunds perform very, very, very well.
So what we generally say at the end of the public field days we've had on site is is for people to not think that these are a silver bullet to cover all the evils of the farm's nutrient losses. And the most important thing to do is to focus on your good management practices. So fundamentally making sure you're not over fertilizing, doing sufficient soil tests, so you're not putting on more phosphorus than necessary. Of course, intensification and matching stock type to stock landform, these are all things that, if they're done wrong, will result in gross loss of soil and loss of soil particles. So, those management decisions and best management practice for managing your soil and your pasture are much more important than a catch-all built at the bottom of your farm. And we always emphasise that the most efficient thing you can do is seriously look at your good management practices and make sure you're getting those.
Oh, well, thank you, John. We've just got one last question around best guess on effectiveness for E. coli. I know you've steered a little clear of this at this moment.
We're kind of hoping that'll be on par with the sediment.
NIWA's investigating that as we speak.
Yeah. So.
I think we'll finish up there. We've just gone slightly over time.
Can I just address that one?
Absolutely. One more
The
question.
Fonterra Living Water Project, they've built a couple of structures. I was in touch with them at the outset, but not once they got started. I don't consider those to be detainment bunds. They're built on sort of retired areas that are out of farming, out of detainment bunds. We're trying to wrap a bit of almost like IP around the name. So on the manual, you'll see the title was Detainment Bunds PS 120. So we're trying to make sure that if people are going to attribute benefits to these structures, and then that benefit is scientifically justified, they need to be achieving that storage ratio of 120:1. So I'm not sure that the Fonterra ones achieve that, and their location is, and where they're located is different as well.
Right. Thank you everyone for attending today. I'll just shuffle in next to JP, you're right. Yeah. And a huge thank you to JP, John Paterson and Brian Levine. We're really, really lucky to have you here for the morning. JP has promised me 2 years ago to do a presentation to New Zealand Landcare Trust, and he held his promise, so we're very lucky. I hope to be sending out an email to you all after this with some extra information. Is that right, JP? From
we can,
some PDFs that you've talked about today?
Yep, we can send out some stuff.
Great. And the potential for perhaps a further webinar down the track for your area, for farmers in your area, to find out more about detainment bunds. In the meantime, keep in contact if you've got any further questions. I'll also send the recording out and the notes and any further notes from this meeting. But thank you all for coming this Thursday, and I hope you have a lovely day and a lovely weekend. Kia ora, everybody.
Thank you.
Thank you.